So today our lecture is fluid mechanics. So first thing, what is fluid? Anything that can flow is called fluid. In fluid mechanics, in fluid, both the things come under like gases and liquid both. Here our analysis mainly will restricted to the liquid. So when you talk about liquid, the term, some basic properties like what is density? So definition of what is the density? It is defined as it is defined as the ratio of mass and volume. So simply we can write density is equals to mass divided by volume. Here m is mass and v is what? Volume. This is about one liquid. If mixtures are there, one more thing, what is the SI unit of density? Its SI unit is kg per meter cube. Commonly few units we use like 1 cc. Cc with the common use. Cc means cubic centimeter. So here it will be equals to 10 to the power minus 6 meter cube. One more common term that we use as a unit for the uh, volume. Cc first what it is. So this 1 liter is 10 to the power minus 3 meter cube. So they will be given the density in terms of, suppose we have given 1 gram per cc. So mostly you have to convert this into kg per meter cube. So this gram I can write 10 to the power minus 6 and cc 10 to the power minus 6. This will come kg per meter cube. So remember, if you have to convert gram per cc into kg per meter cube, directly you can write 10 to the power 3 kg per meter cube. So this is about the density of one, if one liquid is there. Suppose if mixture is there. So density for mixture. So here I can write density of the mixture is equals to mass of the mixture m1 plus m2 plus mn divided by v1 plus v2 to what? Vn. You can write here mi, same thing already we have written. Now we know that density is equals to mass by volume. So this relation also I can write as m1 as rho 1 v1 rho 2 v2 plus rho n vn divided by v1 plus v2 plus vn. We can also simplify this as m1 plus m2 to what? Mn divided by m1 by rho 1 plus m2 by rho 2 plus mn by rho n. If I take for n equals to 2, suppose if two liquids are mixing in a manner that their volume is same. Case 1 if I take, special case it is, otherwise the general formulas are there, you can use it directly. But sometimes we need to calculate fast, and if these two cases, special cases are there, so no need to write. We can write this in one line. So density I can write as density of the mixture if volume is same and density is same. So I'll use the relation 2. So rho 1 V plus rho 2 V by V plus V. So this will become rho 1 plus rho 2 by 2. In case 2, for n equals to 2, but instead of volume, suppose mass is same. So here density of the mixture will become what? I'll use the third relation. So it will become 2m divided by m by rho 1 plus m by rho 2. So it will come as 2 rho 1 rho 2 by rho 1 plus rho 2. I'll take one example. Suppose we have given, if one liquid is there, its density is 600 kg per meter cube, and another liquid is there, its density is 800 kg per meter cube. If they are mixed, condition 1, in equal volume, condition 2, in equal mass, calculate the density of mixture. So in first case, if they are having equal density, equal volume, so what relation I'll use? I'll use the case 1. So what I can write? 600 plus 800 by 2. So this will come 700 kg per meter cube. Second case, what will become? Rho 2 into 600 into 800 divided by 600 plus 800. So 2 into 600, this will come how much? 1400. So done. 4, this is 7. So how much it will be? 4800 by 7 kg per meter cube. So this is what basically the density, how we calculate. So basic relation is what? Density is defined as mass by volume. Then few units how to convert that, what I explained you. Instead of one liquid, suppose many liquids we have mixed. In that case, how to find density? So we have three relations for this. See, in this kind of problem, they will give one. Here we have used three variables, but they will give you only two. And the third one they will ask you. Sometimes they can give you the information mass and volume, density and volume, mass and density, and you have to calculate the density of the mixture. So for that I have taken some special case 1 and a special case 2. If you are mixing in a manner such that volume is same, in that case what will be the density of the mixture? If you are mixing in a manner such that mass is same, what will be the density of the mixture? And based on that I have done one problem, how to use this relation. So that's what I have explained. So after density, we'll come back to, we'll discuss pressure. So what is pressure? So it is defined as the ratio of force and area. Take a surface. On this surface, suppose a force is acting F. To calculate the pressure, we always take the normal component of the force, Fn. Force component we can find by vector. So here we define the pressure. Suppose this area is delta S. So pressure will be the force divided by the area. Or simply you can write S because delta we use normally for the things. So this area is forcefully defined by. Now here pressure is a scalar quantity. What is SI unit for the pressure? Newton. Force SI unit is Newton per meter square. We can also call it this Pascal. 1 Pascal equals to 1 Newton per meter square. So different units are there for the pressure. So simple idea is that what pressure is defined as the force per unit area. It is a scalar quantity. Its SI unit is Pascal. 1 Pascal is Newton per meter square. Now there are different way we measure pressure. Types of pressure. Types of pressure means what are the different way we measure the pressure. So there are three terms we normally write. Atmospheric pressure, gauge pressure, and then absolute pressure. Now if I see atmospheric pressure, what is atmospheric pressure? So pressure exerted by atmosphere on the surface of earth is called atmospheric pressure. When they have calculated this value, 1 atm means 1 atmospheric pressure, it came out as 1.01 into 10 to the power 5 Newton per meter square. This is also equivalent to 76 centimeter of HD. Means whatever the 76 centimeter of liquid column of mercury will exert the pressure, same amount of pressure is exerted by this 1 atm. Now, after atmospheric pressure, the second one we have defined, gauge pressure. What is gauge pressure? When we calculate the pressure of the system by excluding the atmospheric pressure, that pressure is called gauge pressure. Pressure of a system pressure of a system we can write in this some other manner. Pressure of a system pressure of a system minus the atmospheric pressure. Atmospheric pressure is called gauge pressure. Means we don't include the atmospheric pressure term, then it is called gauge pressure. The third one is absolute pressure. Absolute pressure is what? Is equals to gauge pressure plus atmospheric pressure. This is the definition of absolute pressure. So when we define pressure, we define in three ways: atmospheric pressure, gauge pressure, and absolute pressure. Absolute pressure is the sum of atmospheric pressure and the gauge pressure. Now we'll understand how to measure the pressure. So first we'll go in terms of hydrostatics. First we are understanding hydrostatic. So what is hydrostatic? When the liquid is at rest, only liquid way, there won't be any motion in the, there won't be flow of the liquid, but the platform on which it is kept can be in motion. So hydrostatic means what? Fluid at rest. Fluid are not moving. So case one, we'll discuss pressure of a liquid. We can write variation of pressure of liquid in vertical direction. So what it is, let's understand it. Suppose we have given a system. Here liquids are there. And we need to calculate how the pressure is varying inside the liquid. Here liquid is at rest. So suppose I take a small element in the form of cylinder. So here what will happen? Here one pressure will be P. If I say this length is dy, so this here pressure will be how much? P plus dp. So if we take this cylindrical object as a system, so what are the forces?
Here's the Solar System song by Kids TV 123 on Amazon Music.
So here
ये आपके सवाल का जवाब हो सकता है सही जानकारी हस्ती है
here pressure is, force will be Pa. Here P plus dp into A. Here it will be W. So what we can write? P plus dp into A minus Pa. This will be equals to how much? W. So dp into A. W what I can write? dm into G. So dp will be dm I can write rho A into dy into G by A. So dp I can write rho G into dy. Now pressure, if we say, see y change in upward direction, correct? So if I say this point is 1, this point is 2. So from where to where? 1 to 2. Y will change from where to where? 0 to y. So I can write here P2 minus P1 equals to And one more thing here. Here I'll use the minus sign because the pressure change and the dy I have written in a different way, an opposite way. So here when I write this in dy term, so it will be a minus sign here because this p plus dy here I have increased the y in downward direction. So I'll take in reverse way. It will be 2 to 1. So p1 minus p2, because we are moving in downward direction, so p1 minus p2 equals to rho gy. So P1 will be equals to P2 plus rho gy. You can see that pressure in the downward direction is increasing. If at the top surface pressure is equals to P naught. What is P naught here? Atmospheric pressure. Then what I can write? Pressure variation in downward direction at any point P will be equals to P naught plus rho gh. I'll take a very simple example to explain this thing. Suppose we have given liquids are there. At any point A, which is 20 centimeter below. Here atmospheric pressure we have given how much? P naught value we have given 1 into 10 to the power 5 Pascal. So calculate the pressure at point A and B. Suppose this total length is 30 centimeter and this we have given as 12 centimeter. Now if I want to write the pressure at point A, so what it would be? Let's write the question first. Calculate pressure at point A and B. So what I can write pressure at point A. Pressure at point A will be P naught plus rho gh. So 1 into 10 to the power 5, 10 to the power 3 into 10. For A, what is the distance? 20 centimeters. So I can write 0.2. So 1 into 10 to the power 5, I can write 0.02 into 10 to the power 5. So pressure will become how much? 1.0.2 into 10 to the power 5 Pascal. If I want to write pressure at point B, what it will be? P naught plus rho gh. But remember, always the distance will be from the free surface, from the top surface. So how much? 1 into 10 to the power 5 plus 10 to the power 3. From the top, the distance will become 0.18 and g value is 10. So we'll get 0.1.018 into 10 to the power 5 Pascal. So this is what we have learned. In case of hydrostatics, when the liquid is at rest, in the downward direction, pressure will increase. By how much amount the pressure will increase? By rho gy. As you move forward, this much distance, this much pressure will increase. I have taken the consideration, suppose at the top the atmospheric pressure is acting, then I can write at any point pressure is equals to P naught plus rho gh. I have taken one example to explain these two things. So you can understand PA will be equals to P naught plus rho gh, PB will be equals to P naught plus rho gh. Now, variation of pressure in horizontal direction we'll discuss. Variation of pressure in horizontal direction. So suppose same way we'll take a container. In this container liquid is there. So again, we will take a small element in the form of cylinder. So if I say here pressure is P, so suppose this length is dx. So here pressure will become P plus dP. So what I can write, P plus dP into A minus PA will be equals to what? 0. Net force should be 0 because it is at rest. So what I can write, dP should be 0, means P1 should be equals to P2. So we can write in case of hydrostatic, pressure change only occurs in vertical direction, in horizontal direction pressure does not vary if the platform is at rest. I'll discuss what will happen if the platform is accelerating. But here what we can say, in case of hydrostatic, pressure change occurs only in vertical direction. In horizontal direction, what happens? Pressure does not vary if the platform is at rest. So if we take an example, by example, if you understand, suppose we have given a container. In this liquid is there. If I take 4 point A, on the same line there is a B, there is a point C, there is a point D. So here what we can say, as per the things that we have learned till now, pressure at D will be maximum, then pressure at C, pressure at A will be equals to pressure at B. Because in horizontal direction there is no change in pressure. Whatever change will happen, that will happen in vertical direction. So pressure at C will be greater than pressure at A. Pressure at D will be greater than pressure at C, and pressure at A, pressure at B. Now we'll see what happens in case of the platform is accelerating. Variation of pressure in case of accelerating frame. If the frame is moving with constant velocity, there won't be any change. It will be similar to the what you called initial case. Variation of pressure means what? A stationary platform or constant velocity platform. Both would be same. Now see here. Suppose we have given a platform is there on which liquid is there, and this platform is going up with acceleration A. I'll write directly one relation that will cover all the things. So in this case, we write pressure delta P equals to rho into G effective into A. Rho into G effective into H. Here I am writing for. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . for vertical direction. Now see here, if platform is going up, then G effective will be equals to G plus A. A platform is going down, G effective will become G minus A. What about in horizontal direction? For horizontal direction, we'll try to see by derivation little bit different it will be. So try to understand here. Suppose initially liquid was there, it was simply in this manner. And here if we take a small element, now if I say in this direction pressure is P, in this direction P plus dP, and it is moving in this direction with acceleration A. So what we can say, in the direction of acceleration, whatever force is there, that remains that positive as per the Newton's law. So what I can write, PA minus P plus dP into A, this should be equals to dm into A. You know that net force should be equals to mass into acceleration. So this will become how much? Minus dP equals to rho g there's no term g here, rho into area into dx into A divided by A. So minus dP, suppose I take this point as 1, this point as 2. So minus dP from where to where? 1 to 2. So rho, so suppose this length is L. So rho G L. This will become what? P1 minus P2 equals to rho GL. So you can see here, if the liquid is accelerating in the horizontal direction, pressure will vary. So once you start accelerating, its shape will change and it will be in this form. Now after the once liquid start, when this platform start moving, the shape will become like this. Liquid will become inclined. Why it will become inclined? Because due to acceleration, I can see pressure at point 1 is more. So it means the height of point 1 should be greater compared to the, because pressure measured by the height of the liquid. So if I say this height is h1 and this height is h2, so this will become how much? h1 minus h2. So suppose this length is, I need to point, if I say this length is L naught. So what I can write then, this P1 minus P2 I can write as rho G H1 minus H2 and rho G L. So rho and rho done, G and G done. So tan theta will come as H1 minus H2 by L. Wait, G is not there. This is G, this is A. So in that, suppose this angle is theta. So tan theta I can write as h1 minus h2 by L, or this also I can write as A by G. So remember that when the liquid is, when a platform is traveling in horizontal direction with some acceleration A, the liquid will not remain horizontal, it will form a vertical surface. Remember that a liquid forms a free surface in such a manner, there won't be any kind of pressure difference along the free surface. And here the pressure in the horizontal direction, if you draw a free surface parallelly here, then along this surface pressure would be same. What we have seen that in horizontal direction there is no change in pressure. For this means basic idea is that normal to the acceleration, the pressure remains same. So here effective acceleration would be in this direction because G is here, A will be here, the pseudo force. So net effective force in this direction. So you have to draw line parallelly. Here free surface will be inclined to the certain angle, and that inclination will be given by tan theta equals to A by G. What about rotating frame? Pressure variation. In case of rotating frame. So suppose we have given that a frame is there, this platform is rotating in this direction, rotating with angular velocity omega about this axis. So if initially liquid is stationary, once it start rotating, it will form some parabolic shape here. So the rise of the liquid, suppose this height is h. So rise of the liquid with this point center is given by, h will be given by omega square r square by 2g. Based on this relation, many question has been asked. So try to understand h is what? From the point where it is rising. What is the maximum height? And r here will be what? R will be the radius. This. So different point, the height will be different because r is different. So this is what we have discussed, the variation of pressure in case of liquid. Now let's do some question based on this. So first we'll see this question. We have given a cubical vessel of side 5 meter filled with liquid is accelerated with acceleration a. Find the value of a. So the pressure at midpoint m of AC is equals to pressure at n. So what we have given, this vessel is closed and filled with liquid accelerated with acceleration e. So suppose this point pressure is P naught. So I'm assuming that pressure at this point, a corner is P naught. So pressure at n, what I can write, P naught plus rho g. You have seen this in horizontal direction. What we write the pressure in horizontal direction. Oh wait, here it was supposed to be A, L, L. So P1 minus P2 equals to what? Rho AL. So that's what I have written here. Rho A into L. So this is the equation 1. Then they are saying find the value of A. So the pressure at midpoint of M of AC is equals to pressure at N. So midpoint of M, what will be the pressure? First find pressure at C. Pressure at C will be P naught plus rho G L cubical is this, right? So pressure at point M will be equals to PC plus rho A So pressure at C, what I got? P naught plus rho GL plus rho A L naught by 2. Now equate both. This is equation 2. They are saying the pressure at point M is equals to pressure at N. So what I can write from 1 and 2, this P naught plus rho AL equals to P naught plus rho GL plus rho A L naught by 2. Same thing. So P naught done, rho A L naught by 2 equals to rho GL. So rho done, LL done. So A will become how much? 2G. So this will become how much? 20 meter per second square. So this is the thing that what we have done. Let's do one more question. See, we have given this in a tube, liquid filled with this way. Tube is open at end A. Find the absolute pressure at point end B. So if we take a small element here, or directly can do by the formula here, you can write delta P equals to rho omega square R square by 2. Same thing. Here what we have said. Height will vary here. Means you can understand means what if we take a small element, you can use this relation, and this is x. So this way it will come. So what is delta P? Pressure at B minus pressure at A. So what is the value of rho? 10 to the power 3. What is omega value? 100. What is the value of R square? 4. Divided by how much? 2. So 2. So pressure at B, pressure at A is what? Atmospheric pressure. This will come 2 into 10 to the power 5. So this will come 3 into 10 to the power 5 Pascal. Let's take this question. We have given a U2 filled with liquid is being rotated about an axis with an angular speed omega as shown in figure. The difference in height of the liquid in 2 arms. So as per the formula, what I can write h1 equals to, suppose this one I am representing as, it has rises to certain values, h1. So h1 will be how much as per the formula? Omega square r1 square by 2g. Here h2. So suppose this height is h2. So h2 what I can write? Omega square r2 square by 2g. They're asking difference in the height. So delta h will become how much? Omega square by 2g. R1 square minus R2 square. So which option? Option A. Now after this we have understood how the pressure varies. This thing. Now we'll go for the mechanism to measure the pressure. Pressure measuring instrument. So the first thing that the basic thing is barometer. So what is barometer? A container is there. In this container, suppose some liquid is there. How they constructed this barometer? Then they have taken a here also they put a mercury. Why they have used mercury? Because the most dense liquid available. I'll explain what will happen if we take some other liquid. Next stage, what they did, they put these two things, this one they have inverted in this container. So here finally situation is like this. So if we invert it into this, liquid rises to certain height. Suppose this height is h. So since here whole liquid was there, mercury was there, so nothing is available here which can exert the pressure. So pressure at this point I can write as a 0. And we know that in statics, in hydrostatics, liquid does not, pressure does not vary. So if this is P naught, this point pressure will also be P naught in horizontal direction. So what I can write then, P naught equals to, P naught will be equals to top pressure is 0, rho GH. And when they measure this value of H, they figured out this is 76 centimeter of HD. So 76 centimeter, the height was, I'm writing only H, so write only value. Now thing is that what will happen if I use some other liquid, like if I use water. So try to understand that density of mercury is 13.6 times denser than the water. So if I use water, this height will become how much? 13 times, 13.6 times of this value. So you can say making a this made of water this much very height, it won't be possible. So that's why we went for the liquid, means the height will be small and it will be easier to do. So that's why we use the mercury instead of any other liquid. So after barometer, the other device is there which is used to measure the pressure, manometer. So basically you can write as U2 manometer. So what is U2 manometer? In U2 manometer, we can measure the pressure of any closed system. In U2 manometer, one end will be open and one end will be connected to the system. So here what is the situation? Here the situation will be in this manner. So you can see the one end is connected to the gases or system and the other end will be open to the atmosphere. So what will happen? Whatever is the gases inside, they will exert some pressure. Suppose in this manometer some other liquid is there. Now this is the reference line where these two are meeting. So if I measure this height will give you the pressure of the liquid, because pressure of the container, the system. Because at this point they are in equilibrium, means this pressure and this pressure and this point pressure would be same. So if I say this point as A and this point as B, so PA will be what? Pressure of the system. We can write PA will be equals to what? PB. So what I can write, PB equals to P naught plus rho GH. This is how we use U2 manometer to calculate the pressure. Some different applications are also there. Suppose I'll take one question. We are given one U2 manometer is there. Suppose in this section there is some other liquid, and the other section, in the two section, two different liquids are there. Suppose this liquid have density of 0.9 gram per cc, and this one have density of, this is rho 1, 0.6 gram per cc. Suppose from the reference line, the point of at the interface, if this height is 40 centimeter, what will be the pressure, what will be the height in other section? So we can use the concept that in horizontal direction the pressure should remain same. So whatever is the pressure at this point, same will be the pressure at this point. So if I say this point is A and this point is B, I can't say, means what, if I draw a line, I can't say pressure at this and pressure at this would be same, because these two are different liquid. But interface, if I draw similar liquid, so I can say pressure at A and B and same. You can ask why I'm not drawing here. If I draw here, unnecessarily I have to calculate this height and this height. So that I don't want, means it will be cancelled out, but unnecessary extra part will be there. So that's why always take the interface at the line. So what we can write here, we can write here pressure at point A should be equals to pressure at point B. Pressure at point A, I can write rho naught into G into H1. Pressure at point B, rho 2 into G into H2. P naught done. So rho 1 H1 should be equals to rho 2 H2. Rho 1 is how much? 0.9 into 40. Rho 2 is 0.6 into H2. So this will come 2. This will come 3. This is 20. So H2 will be equals to how much? 60 centimeter. So this is how we'll deal with the problem related to U2 manometer. Let's take one example. See, we have given, it is a similar problem, so there is no benefit. So we have seen this till now, the how we can measure the pressure, what is the value of pressure in case of different, in many cases, different type of cases we have seen. So after this hydrostatics, this pressure and all the things in the hydrostatic, our last concept would be buoyancy force. So what is buoyancy force? So before I start this one, a small concept is there, that Pascal law. Pascal's law. So what is Pascal's law? It said that in case of hydrostatics, in case of hydrostatic, if there is a change in pressure at any point, same change will be reflected at each and every point. So what I said here in Pascal's law, it says that in case of hydrostatic, if there is a change in pressure at any point, same change will be reflected at each and every point. So let's understand it. Suppose we have a container. In this container, some liquid is there. Suppose this is closed here and applying a force F here. I take two random points in the system, A and B. So if these 2 points height difference is h, so what I can write? PB minus PA will be given as rho GH. See here, density of the liquid constant. Here we are talking about in fluid mechanics. We discuss about the liquid, which density remains constant, means it is incompressible. So density is a constant here, G value is a constant here, and incompressible, so H will remain constant here. So if suppose I apply a force F here, so at this point, if some change is there in the pressure is P prime, because if you apply the force, there would be some change in the pressure. So since PB minus PA, the difference should remain constant. So whatever pressure change is reflected at point A, same amount, same change should reflect at point B. Then and only then this relation will hold true. So this is what the Pascal's law says, that in case of hydrostatics, if you change pressure at any point, same amount of change will at each and every point of the liquid. So that is what Pascal law. Now comes to the buoyancy force. So what is buoyancy force? When an object is partially or fully submerged in a liquid, then an object is partially or fully submerged in liquid, then an upward thrust act on it. This force is called, this upward thrust, this force is called buoyancy force. Why this force coming to play? This force is due to pressure variation in the liquid. Let's understand it. Suppose any object is there, it is partially submerged in a liquid. So what we can say on this, forces will act, always force will be due to the pressure normal to the surface. And you know that in downward direction, the pressure is increasing. In downward direction, pressure is increasing. So I can say the downward force will be more. Means so these forces will be larger compared to these forces. So what will happen? They ultimately push the object upward. This leads to the buoyancy force. So what is the value of buoyancy force? The magnitude of buoyancy force is equals to weight of weight of liquid displaced by the object. This statement is called Archimedes Principle. What is Archimedes Principle? It says that the buoyancy force that is acting on this object due to the pressure difference, it will be equals to the weight of the liquid displaced by the object. And this statement was given by Archimedes. So this is called Archimedes Principle. So this is about the buoyancy force. So what will be the magnitude of this buoyancy force? So buoyancy force we write density of liquid, volume immersed into G. So volume immersed inside the liquid, immersed in the liquid. I'll explain you this concept by an example. Suppose we have given if this object is 50% part is inside bottle. If V immersed is 0.5 times of total volume and density of liquid is 900 kg per meter cube. Calculate the buoyancy force. We have given here information V naught is 100 centimeter cube. Density of liquid is already there. So what I can write? The buoyancy force is equals to density of liquid into V naught into G. Density of liquid we have 900. It's not V naught here, here V immersed. So how much I can write? 0.5 into 100 centimeter cube. Centimeter cube convert into meter cube. 10 to the power minus 6 into 10. So this 10, this decimal will be done. These two, 10 to the power minus 2. So how much this will come? 0.45 Newton. This is how we are supposed to calculate the buoyancy force. Let's do some question based on this concept. See, we have again a boat is there having a length of 3 meter and breadth of 2 meters floating on a lake. Boat sinks by 1 meter when the person gets on it. So they're asking the mass of the man. So the buoyancy force, the extra buoyancy force when the person will climb, that will be given by how much? Density of liquid, volume immersed into G. So water is there, water density is 10 to the power minus 3. How much volume it will sink? So 3 into 2 and 1 centimeter is height, right? So 1 into 10 to the power minus 2. What is the value of G? 10. This buoyancy force should be equals to what? Mg. So this G and G will be done. So what I can write? M. This will come 10. So 60 kg. So which option? Option A. Let's take one more question. So we have given this. They have given that a sample weight 210 gram in air. So air is mere weight is how much? 210 gram. 180 gram in water. So 180 gram. And 120 gram in unknown liquid. 120 gram. So in water, what we can write? In water, buoyancy force will act and downward direction weight will act. So this relation I can write the weight of the liquid minus the buoyancy force. This is equals to 180 gram. And WA we have given 200 gram. Basically, it is in terms of mass, so you can write by G divided by G because they have given in terms of mass. So what I can write? FB by G will be equals to how much? 30 gram. So density of liquid into volume immersed into G divided by G. This is equals to 30. So done. So I can write density of liquid in terms of density of water in terms of grams is H1. So volume immersed, how much will you get? 30 cc. So they're asking that which of these statements are correct. So if I first they're asking density of the metal. So what I can write from this statement, I can write from here. Let's write it separately. So we have given Ma is equals to 210 gram. So density of object into volume of object is 210. Volume of the object we have get this. So density of object will come out how much? 7 gram per cc. So this one was not matching. Density of metal is how much? 7 gram per cc. So density of metal is 4 times the density of unknown liquid. Let's check what will be the density of unknown liquid. So if I say, if I compare these two terms, so what I can write? WA minus FBL, that is given as how much? 120 gram by G. So what I can write? Buoyancy force in the liquid by G. This will come 90. So this density of liquid into volume of the object is 90. So density of liquid volume of the object I got 30. So this will come 3 gram per cc. So this statement is also wrong. One is 3, other is 7. It is not 4 times. Metal will float in water. If it is floating in water, net buoyancy force, net force will become 0. So this is how we approach the question related to the buoyancy force. So till now we are discussing regarding the fluid statics. Now we'll go for the fluid dynamics. When the fluid are in motion, how the pressure and everything will be affected, that we'll try to learn here. So what are the types of flow can be there? So types of flow. First one is steady flow and unsteady flow. So what is steady flow? If we say steady flow, suppose we have given any tube through which liquid is flowing. It says that if it's the flow is steady flow, so if a steady flow is there, any cross section you take. So we can write for any cross section, del v by del t will be 0. It means what? Any particle which is coming here will have same velocity. It may have different velocity here, but at any cross section with respect to time, there won't be any change in velocity or any other parameter. And for unsteady flow, I can say del v by del t won't be equals to 0. So this is the thing, difference between steady flow and steady flow. Same way there is uniform flow and non-uniform flow. So what is uniform flow? If we say, if I say uniform flow, if the liquid flow in a manner such that at each and every cross section their velocity is same at a given instant of time. So there I say delta v by delta t should be 0. But here with respect to time they may vary, but with cross section, at any cross section, at any time, del v by del x should be 0. Means velocity should not change with respect to time, with respect to the position. What is non-uniform flow? Non-uniform flow. So non-uniform flow we can say del v by del x will not be 0. Flow means at any point the velocity could be different. So that is called non-uniform flow. And then we have laminar flow. If the fluid particles flow in a layer, then it is called laminar flow. Try to understand what is the meaning of this statement. See, every fluid particle will follow a constant path. Means what? Intermixing will not happen. Two fluid particles will not intersect their path. So here they flow like a layer. Here they don't interfere in the other particle's path. So this kind of flow is called laminar flow. We can write here fluid particles follow a constant path in laminar flow. The path of this fluid particle is called streamline. Tangent on a streamline gives the path of, gives the direction of flow. So these were the points regarding the laminar flow. Then we have turbulent flow. If the flow is random, you can't decide what will be the path of the particle or a thing. If the particle flow is not, path is not fixed, if fluid particle follow zigzag path or the motion is simply we can write that the flow of the for a zigzag path, and then the flow is called turbulent flow. Here you can't decide about what is going to be the path of the particle. It's just random. So that's why it is called random flow, turbulent flow. So these were the types of flow in case of fluid mechanics. So we have discussed steady flow, unsteady flow, uniform flow, non-uniform flow, laminar flow, and turbulent flow. Now we'll come to equation of continuity. So what is equation of continuity? It is simply conservation of mass. I'll explain by an example. Suppose in a tube, liquid is flowing, and this will say cross section A, this is say cross section B. This is A and this is B. So it simply say that it is simply conservation of mass. So whatever the mass delta MA, this should be equals to delta MB. Suppose here velocity was V. So what I can say here, if I take a small section here, so this section length will be how much? V dt. Suppose its area is AA here, I can directly write. So delta M, what I can write? Density of liquid into the volume. Volume, what I can write? Area at A into velocity at A into dt. Same way, if I take a small element here, it will be what? VB dt. It was VA dt. So I can say this mass, whatever is going out of the section, that should be same from conservation of mass. So rho into area of B into VB into dt. Density will remain same as it is in incompressible liquid we are discussing about. So AA into VA will be equals to AB into VB. This is what equation of continuity. Here area into V one term we'll use is area into velocity. Here the term Q is discharge. Discharge is volume per unit time. This is the Q. A is what? Area. V is what? Velocity. So basically it says that the discharge, if in a case of in case of ideal liquid means what? That in it should be incompressible, it should be homogeneous, it should be non-viscous. In that case, the discharge will remain same. Means V into A will remain constant. Equation of continuity is also it is conservation of, you can say conservation of mass. After this we have Bernoulli's equation. What is Bernoulli's equation? We need similar diagram. So here suppose this height we represent as HA, this height we represent as HB, and with respect to the height this thickness is very small. Now what is said Bernoulli's equation? It says that for an ideal liquid, for an ideal liquid, sum of potential energy kinetic energy and pressure energy remains constant. This is a very Bernoulli's equation and it's really useful. Many questions would be asked based on this. So what is basically it is? It says that pressure energy, kinetic energy, and the potential energy, this should remain constant. Or we can say pressure head, kinetic head, and the potential head, that should remain constant. Here P reflects here pressure head half rho V square, this is called kinetic head, and rho Gz, this is called potential head. So basically you can understand in this way, whenever in case of an ideal liquid, the sum of P half rho V square plus rho Gz, pressure head, kinetic head and potential head remains constant. How this relation comes? This comes relation from the Bernoulli's equation. It says that the sum of potential energy, kinetic energy and the pressure energy remains constant. So let's understand these with few examples. See, we have given at Dev-Prayag, Alaknanda river, Alaknanda mixes with the river Bhagirathi and becomes river Ganga. Suppose Alaknanda river has a width of 12 meters. So suppose river was there 12 meter. Bhagirathi has a width of 8 meter and Ganga has a width of 16 meter. So this is the thing. So they are saying that at Devrayag, river Alaknanda mixes with river Bhagirathi. So Alaknanda, how much is the difference? 12 meter. Bhagirathi has a distance, how much difference? Width 8 meter. This one has a width, how much? 16 meter. They are saying assume the average speed in Alaknanda is 20 kilometer per hour. And in Bhagirathi is 16 kilometer per hour. Then they're asking what will be the speed in case of river Ganga. So same idea. Suppose I am taking this as 1, this is 2, and this is 3. Equation of continuity. So what I'll write? A1 V1 plus A2 V2. This should be equals to A3 V3. So area will be what? Whatever width into thickness, they have mentioned that depth is same in all the three rivers. So A1 I can write as 8 into whatever the thickness depth is there. So T into 16. A2 I can write 12 into T into 20. This I can write 16 into T into V. So T will be cancelled out. So V I can write 128 plus 12 into 20 it was. So 240 divided by 16. So this will become our velocity. Now let's take one more. See, they have given there is a small hole at the bottom of a tank filled with water. There is a tank, it is filled with water. And there is a hole at the bottom. So they're asking if the total pressure at the bottom is 3 atm, 3 atm, then find the velocity of water flowing from the hole. So one point, whenever you have to write the Bernoulli's equation, you have to take two cross section. So one cross section, one area I'm taking just above this, one is just outside. So just above this, there won't be any liquid flow, it won't be moving. So P1 plus half rho V1 square, velocity would be negligible. This will be equals to P2 plus half rho V2 square. You can see that this area is very large compared to this area. So from equation of continuity, you can say velocity at point 1 will be very small compared to velocity at point 2. That's why I will not consider this. So I can say approximately it would be 0. So P1 we have given 3 atm. P2 is just outside this point, so here atmospheric pressure it would be P0 plus half rho V square. So I can write rho V square by 2. This is equals to how much? 2 into 10 to the power 5. Then I can write rho V square, this will come 4 into 10 to the power 5. Rho we have how much? 10 to the power 3 into V square equals to 4 into 10 to the power 5. So this will come, so velocity will become how much? 20 meter per second. This is how we are supposed to use Bernoulli's equation. Let's take one more example. We are given this, they're asking In the figure shown, find the range R. So I'll take a reference line. So this is our reference line. And remember that in Bernoulli's equation, you can write equation only between same liquid. You can't write between one point I'll take here in this liquid, one other point I'll take in this liquid. No, it will not work in that manner. Both the point about which you are writing the Bernoulli's equation, both should be same. So one is this and two is this. So what I can write from Bernoulli's equation? Already they have mentioned 1, 2. So I'll take this as A. Just this point is A and this point is B. So PA plus half rho VA square plus rho GHA equals to PB plus half rho VB square plus rho GHB. What is the pressure at point A? P naught plus rho GH. See this point is just, so P naught plus rho GH. Velocity at point A, I can neglect this term to become 0 because area is very small, so 0. This rho G into H, this PB will become P naught plus half. What is the density of the liquid which is coming out? 2 rho into V square. Rho G H3 will become how much? It is on the same, this is the reference line. So this will become 0. One thing here is this. When I am writing rho GHA, this liquid density is 2 rho. So 2 rho GHA. With respect to reference line, how much height is it up? H. Now see this P naught done. So what I can write? Rho V square equals to 3 rho GH. So rho and rho done. V will become root under 3 GH. But they're asking, we got velocity, they're asking range. So range, what I can write? Range will be equals to velocity in x direction into time. Velocity in x direction, how much I got? Root under 3 GH. And time will be given by 2h by g, height is h1. So this one done. So this will become how much? Root under 6h. Not root under 6h, h will be outside. So this will be equals to root 6h. So this is how we are going to use Bernoulli's equation. See, after this, we are going to start properties of the liquid. So first thing, surface tension. So what is surface tension? It is the property of liquid by virtue of which it minimizes surface area. You would have seen that a liquid droplet always in the spherical shape. You will never find a liquid droplet in the form of a square, in the form of cube, or any other shape. Why? Because for a given geometry, for a given volume, surface area for a sphere would be minimum. That's why they acquire always in the form of spherical shape. So what is surface tension? Surface tension, it is a property of liquid by virtue of which it minimizes its surface area. So try to understand, suppose any liquid surface is there. On this, if we draw a line, it will act like a stretched membrane due to surface tension. free surface of the liquid acts like a stretched membrane. Now, suppose this is the surface of a liquid. If I draw a line, so what will happen? If we try to think, if any rubber is something is stretched, they will try to pull. So on this both side, due to surface tension, a force F will act. If I take this part as length is L, so we write mathematically the surface tension S is equals to force divided by length. Force acting on this part. Here S is what? Surface tension. L is length. F is force due to surface tension. I'll take one example to explain this. It is we have given a 5 centimeter long straight piece of thread is there. It is kept on the surface of water. Find the force with which one side of the thread will pull it. So surface tension I know, force by length. So force I can write surface tension into the length. They're asking only one side, right? So otherwise net force would have been 0. So surface tension we have given 0.076 and length is how much? 5 centimeters. So 5 into 10 to the power minus 2. So this will come how much? 70 into 5, 350 and 380 it would be. So 380 into 10 to the power minus 5 Newton. So this is the thing. Let's take one more problem for this. See, then we have given a thin liquid formed between a USF wire and a light slider support a weight of 1.5 into 10 to the power minus 2. The length of the slider is 30 centimeter. Its weight is negligible. The surface tension of the liquid film. First, try to understand what is the problem. Here, the surface is there. So, if this weight were not there, they will try to minimize its surface area. So, it would have been gone up. It is here in equilibrium means what? The W which is applying a force that should be balanced by what? This force which is acting up. So I can say surface tension force should be equals to weight, and try to understand one surface is there on the top, one surface would be there on the bottom. So 2SL should be equals to W. What they're asking surface tension. So 2 into S, we have given length as 30 centimeters, so 0.3. What is the weight of the liquid? Weight of the support 1.5 into 10 to the power minus 2. So this will become 5. So S will become how much? 2.5 into 10 to the power minus 2, and unit of surface tension will become how much? Newton per meter. So which option is correct? Option D. After surface tension, we'll discuss surface energy. So what is surface energy? Liquid particles at the surface are having more energy compared to liquid at the bottom. So try to understand, if a container is there, in this container any liquid which is there on the top, so what happens? This liquid may escape because they have extra energy. So any liquid which is at the bottom here, on this, the since place is there, so liquid from the bottom will go up. So when they are going up, some work is being done on these liquid, because see on the here the forces will be in this manner. And if I take a droplet at the bottom, and this process will be same. So when a liquid goes up, it has to do work against the gravity, against the surface tension, cohesion force. So because of that, a the liquid droplets on the surface will have more energy. So this lead to the surface energy. So surface energy is defined as surface tension per unit area. So wait, not surface energy we defined as S into A. What is U here? Surface energy. S is surface tension and A is area. So let's do few problem based on this also. Now see if they're asking find the surface energy of water kept in a cylindrical vessel of radius 6 centimeter. So what I can write the surface energy? Surface energy equals to surface tension into area. So 75 into 10 to the power minus 3. What will be the cylindrical surface? So radius will become, area will become how much? Pi r square. So pi into 36 into 10 to the power minus 4. 75 pi into 36 into 10 to the power minus 7 joule. So based on this, there are few things on surface tension we should understand. Pressure inside a liquid droplet. So any liquid droplet is there or air bubble is there. If inside pressure is P1, outside pressure is P2. So here we write P1 minus P2 is equals to 2S by R in case of liquid droplet or air bubble. But pressure in case of pressure in a soap bubble. You would have seen the soap bubble in childhood. We do this thing is what we make this soap bubble with some arrangements. We would have done this activity. So here two layer a very small thickness it would be having. So suppose here pressure is P1, here this section is 1, this is 2, and this is 3. So we can write P1 minus P2 equals to 2S by R. Same way, P2 minus P3 equals to 2S by R. If I add them, it will become P1 minus P3 equals to 4S by R. Remember, in case of soap bubble, the pressure becomes 4S by R. After this, we will go for capillary rise. So what is capillary rise? See if any container is there in which water was there. So in this container, if you keep in a container, if you keep a very small tube, tube having very small radius, so you'll observe that this liquid has gone with for certain height. So this is called capillary rise. So why does it happen? This happen because of the surface tension and angle of contact. So before I explain you this capillary rise, one concept is there that is called contact angle. So what is contact angle? So if you keep any liquid droplet on a water surface, on a solid surface, so if you draw a tangent here, so here the angle it forms, this is called angle of contact. If you draw a tangent, try to understand. Sometimes this contact angle is lesser than 90-degree acute. So in that case, what happens? The liquid goes up. So here if you see, if I draw the tangent here, one will be here, one will be here. Remember, whenever you draw tangent on the solid, it should be into the liquid. So here theta is lesser than 90-degree. Here liquid will rise. Why liquid will rise? Because of surface tension, our net force will be there in upward direction. Sometimes the same theta will be zero also. In that case, there won't be any rise in the liquid. The contact angle is 90-degree. So in that case, what happens? There won't be any increase. Theta is equals to 90-degree, no rise. But if theta value is greater than 90-degree, what will happen? In this case of rise, instead of rise, liquid will depress. Here if we see, so liquid will go down. So here the theta contact angle is greater than die. Here liquid will fall. Fall means with respect to another surface it will go up. So capillary rise, because of the contact angle, what happens? The liquid here it goes up. So we need to figure out what will be the value of H. So if we calculate due to surface tension, liquid rises by certain height. So here if we calculate the height, this will be given as 2s by rho rg. This is called capillary rise. Same thing you can use if the liquid dip in case of if theta is more than 90-degree. Here instead of rising, liquid will go down. Here also this H will be given by the same thing. H will be equals to 2s by rho rg. This is basically here 2s cos theta. 2s cos theta. In case of water, theta becomes 0 degree. So H is 2s cos theta by rho rg. Now after this the another property of the liquid is what? Viscosity. So what is viscosity? Frictional force it is the property of the liquid by virtue of which it opposes the relative motion between two layers of the liquid. Simple idea, when the one layer try to move over the other layer, due to this property of the liquid, it opposes the flow. So here this viscous force is proportional to the velocity gradient. This viscous force is proportional to the area. So if we combine these two relations, you will get as F equals to minus neta A into dV by dx. What is dV by dx here? In dV by dx here, velocity gradient. Here A is what? Tangential area. Try to understand this. Suppose this point have velocity v, this one has v plus dv. I say this separation is dy, write it in vertical direction, so write it as a dy. So we write, and this is the idea, v velocity gradient, whatever the difference in the velocity between two layers, and area will be what? Tangential area, this area over this thing. So that is called, that will be included in the viscous force. After viscosity, we have one Poiseuille's relation. What it says? It says that if liquid are flowing through a tube, if liquid is flowing through a tube, then discharge through it will be proportional to pressure gradient. Suppose this length is L, and here on this cross section pressure is P1, on this cross section pressure is P2. So this discharge here, Q is what? Discharge. If you remember, area into velocity. What is delta P? Pressure difference. And what is delta P by delta L? Delta P by L or delta P by delta L? Here it is called pressure gradient. Q is also proportional to neta. Q is also proportional to R. So if you combine all these three, we get the equation pi delta P R to the power 4 by 8 neta L. This is the equation Poiseuille has given. It is applicable for what? When the liquid are flowing through a tube and we have to calculate the discharge. After this, we have Stokes Law. What is Stokes Law? It dictates if a solid sphere, suppose a sphere is there, It is moving inside the liquid. So it says that here force on this will be proportional to the radius. It will be proportional to the velocity. It will be proportional to the viscosity. So here the force comes 6 pi neta RV if we include all these things. Stokes law, this what says that if a solid sphere, right, a sphere only, doesn't matter whether solid or not. If a sphere moving inside a viscous liquid, viscous liquid, then force on it is proportional to radius, velocity, and the coefficient of viscosity. Now after this we have, by combining this Stokes law and the buoyancy force. So try to think, if I drop a sphere with certain velocity, or simply in a liquid and with zero velocity, if its density is more, what will happen? Initially buoyancy force will dominate. Sorry, initially gravitational force will dominate. Buoyancy will try to oppose, but if it is the sphere is denser, then it will apply a constant force. But what, due to Stokes law, what will happen? As the velocity will increase, the viscous force will increase. So after some time, its velocity will become constant. That is called terminal velocity. Terminal velocity. When a sphere, when a sphere, not right, simply when an object is dropped inside a liquid, its velocity increases for some time. After a certain time, after certain time, its velocity becomes constant. This velocity is called terminal velocity. Try to think, if a sphere is there, on this sphere, what are the forces will act? Buoyancy, viscous upward, and mg downward. So what I can write, viscous force plus buoyancy force, this should be equals to mg. Viscous force, what I can write, density of object, sorry, density of liquid into volume of object into g. Viscous force will be 6 pi neta r into v. Mg will be density of object v naught into g. So 6 pi neta rv, this I can write as rho naught minus rho l into v naught into g. So v I can write as how much? Rho naught minus rho l into v naught into g by 6 pi neta r. This v here is the terminal velocity. Here in this thing, one term is unknown that I have not explained, neta. This is called coefficient of viscosity. That's what we are using again and again. So this was the regarding the lecture for the fluid mechanics. So it's over. Thank you.